So we will start off with the session. Hope you had good time at home, right? Okay. And at least one day you could do whatever you could do, whatever you wanted to do. So it's fine. Again, you are back in the campus. So when is the trip, Sastra trip? It is on this coming Wednesday. So when you are back, I think there must be some projects, the titles and the mentors have to be fixed. And once you are back, you will be starting that. Probably they will be circulating the forms once the project titles and mentors are ready. Then you may have to fill up according to your choice. They may give choice 1, choice 2, choice 3 for you. It's most likely that your choices are not the ones that you get. Okay, so it is kept that way. So, right? Anyway, so okay, so that day we were discussing about conformational analysis, right? So we use very simple systems such as we started off with ethane and then went to propane. Then we stopped at butane. We gave something for you to think about and then come back, right? So in this particular session, I have simplified as much as I can. Okay, so there may be a lot of information that is in the slide. Of course, you can stop me at any time and we try to elaborate more on it. Yeah.
So is this actual literature that
this is the work that has happened in our laboratory.
and it's published?
It is published, and you will understand the intrinsic aspects of conformational analysis and so on. Along with that, there's some literature background for you to dig more on. So that is the lecture. So what, as per the title says, there is strained to perform. That means to do an action, you have done something, which means you have probably strained in order to make the system perform. Right? And how did you do that? We did by conformationally locking. Conformational locking was one of the aspects. And M-cyclophane is one of the molecules that we are going to deal about. And it is a crown basically. It's kind of a crown. This molecule possesses a crown shape. So the moment you say crown, there is a void in between, right? There is a space in between. And that cage is actually C60. Most of you are aware about C60, right?
Yes, sir.
What is that? That is a Buckminster fullerene. So the shape of it is like a soccer ball, right? Like a football. So it's a spherically shaped aromatic hydrocarbon. And that we try to put it in the space available within the cone shape of the molecule. Similar systems that are existing in the literature. So these are basically macrocycles. They are called as macrocycles. The structure that you are seeing here has 6 oxygens, right? And there are 12 methylene units. Between 2 oxygens, between 2 oxygens you have 2 methylene units, right? So it is the name of this molecule is crown ether. There is a ethereal linkage. Ether is, you have alkyl groups connected to oxygen, then you call that as dialkyl ether. Right? So similar of such structure you are seeing here, both the side you have methylene and oxygen is connecting those two. Right? This molecule as such is very, very flexible. Okay. When you put them in solution, they are undergoing conformational motions. Right? So these methylene groups can go below the oxygen and then they can push back and forth. So you will have deviations from planarity. And this is a cage type of a structure, as you can see. It's a cycle, and it has oxygen. So any cations, if you put in, if the size is appropriate to be captured within this available space, then those cations are captured. Okay. So this particular size, which you name it as 18 crown 6, because when you count all the atoms there are 18 atoms. with 6 oxygen atoms that are present there. So name is 18, crown, and 6. Okay. Yeah.
Sir, you had mentioned that this is a macrocycle.
Yeah.
Molecule.
Yeah.
What are macrocycles?
Macrocycles or the cyclic, they possess the cyclic structure, and these are molecular entities that can complex certain ions or certain molecules. It can also exhibit the recognition property, which nowadays is popularly called as sensing. It can also sense.
What
It-
is the recognition property?
It can also recognize the molecules.
What is the
Recognition
recognition?
means, yeah, in some cases it could be ions, some cases it could be molecules as such. Okay. So, if such structures are usually called as macrocyclic structures, they have a cyclic structure as such.
So, I still don't completely understand what recognition means. Does it just mean it can react with other molecules?
No, it doesn't react, right? It establishes a specific type of interaction, right, to the incoming guest. If you want to call this as a host and the guest is coming in, there is some kind of a stabilizing interaction that this host molecule provides to the guest and thereby tries to stabilize, and it forms a complex ultimately. Okay. So that is the recognition. And why we say recognition, because the size is more important, we said. So the sizes are of for all of different types you have, right, ions, then it would just recognize the particular ion which can fit into the cavity or the available space. So it can recognize a particular ion of appropriate size within this cavity. So that's why it's called molecular recognition. Yeah.
Can you please give an example of this recognition, sir? Like a reaction or a...
Yeah. So you take this macrocycle, let's say you put a potassium salt to it, add a potassium salt to it, KCl for example, and it will capture only the K plus ions. Okay. One K plus ion sits between this all oxygens. Okay. Oxygen has the lone pairs, and if it is a potassium ion, it is K plus, so it is deficient in electron density right now, and oxygens all would donate this lone pairs, and it would establish a stabilizing interaction. Okay. So it is a complexation. So at the end of it, if you want to isolate, you will isolate the potassium ions alone, right, by this using this crown ether. So it will form ultimately a complex of crown ether plus K plus. It will form a complex. So various, when I say interactions could be of different types. Here we saw ion is binding. You can also think of an electron rich molecule recognizing an electron deficient molecule. Okay. So thereby you have a donor acceptor kind of an interaction. You can also think of two dipoles coming together, dipoles of positive, negative, holding another molecule in an opposite way with positive with negative and negative with positive. So dipole interactions, ion dipole interactions, ionic interactions plus with minus, right, and donor acceptor pi type of an interaction are all possible. So that is why this particular area is called as supramolecular chemistry. Yeah.
Between the crown ether molecules, this 18 crown 6 molecules, is there like, does
Molecular interactions.
Hydrogen bonding also play a role?
Hydrogen bonding is known in similar systems,
Okay, but not in this.
not in this one. Here it is an ion interacting with an oxygen dipole, heteroatom, right. So this is the interaction that this particular macrocycle introduces, and the photograph that you are seeing there is Pedersen, who shared a Nobel Prize with Jean-Marie Lehn for this particular development. Okay. So this is the very first molecule known, I would say, 1960s, characterized by Pedersen. The other Nobel laureate that you are seeing here is Jean-Marie Lehn, who shared the Nobel Prize with Pedersen, of course. Okay. What he did was, he slightly modified the system. He put another anchor to the crown. As you can see, he had added one more arm, right, to this particular structure. Just that you do not have oxygens there, he had put two nitrogens because it can provide 3 valence, right. So he had connected this. Nevertheless, he kept the oxygen to capture the ions, but now these ions are captured in a cage. So it's not that easy to knock them off. Okay. But on the other hand, here, this weak interactions, this ion and the oxygen interactions could be broken by several means, right? You can change the pH, you can knock them off, increase the temperature, you can destroy these weak intramolecular hydrogen bonding or interactions, right? You can easily destroy them. So several forces can operate. You can assemble and you can dissociate also, right? So that was possible. Now since Jean-Marie Lin has added one more arm, now it is like a cage wherein these cations sit in between, and it is very difficult. It's not that easy for you to push them off. Okay.
So are these synthetically prepared?
These are synthetically prepared in the laboratory.
They are not found anywhere now.
They are not found anywhere. These are synthetically made skeletons.
What's like their application?
Huh?
Application.
Application is to capture ions, right? So for example, toxic metals are there and you want to just capture these toxic ions, right? That's where their implications come. So very important skeletons. Yeah.
So sir, can we also use this in like nuclear reactions, sir, where it can capture neutrinos or neutrons or anything like that, electrons?
But you can capture the radioactive ions.
Yes, sir. So this is applicable.
Yeah, you can do that.
Yeah, has it been done before, sir?
It is done.
Okay.
There are various other methods, but I'm not sure whether they are using the exact skeleton for that purpose. But the modified versions of them are surely in place.
Yes, sir.
Okay. So extraction of, because whenever you do, in particular in that case, radioactive ions such as lanthanums and uranium ions, which are coming out of the industry, you can just pass this through it in a fixed bed. These ions are trapped, and then the remaining portion of it is let out. Okay, which is not harmful to the environment. So for that applications, such kind of scaffolds are very, very useful, right? So the modification is introduced by Jean-Marie Lin as a development. He calls those structures as cryptands basically. So from crowns to cryptands, it is modified. Okay, crypt in a sense, it's a cage. So the word has a meaning of cage. So he used this cryptand as a terminology. Okay. So then came another structure. This is very much known long before than when crown ether was introduced to the community. But most of the times product formed, but there was no identification of how the molecule looks like. Because those days characterization techniques were not grown, right, that much. So some elementary characterization could be done, but they couldn't arrive at the structure per se. So nowadays we know the structure of this, right? This is a glycouryl moiety at the center, and it just condenses with formaldehyde, right? And forms a kind of structure that you are seeing here, which has 1, 2, 3, 4, 5, 6 of the glycouryl units held by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 of the methylene bridges. So the structure as such, if you see, it is very similar to that of a pumpkin structure, that's, So they have this because pumpkin falls under the category of Cucurbidaceae family. So the name came as cucurbit urals because they're made of glycouryl units, right? And this structure, if you see, the middle part of it is particularly hydrophobic, but the top end is surrounded with oxygen, which is dipolar in character, right? And the bottom portion of the oxygens are also having carbonyls, and they are also dipolar in character. So the top end and the bottom surface, both of them are polar in character, leaving the central part as non-polar in character. So what could be encapsulated into this cavity is only the non-polar molecules. or molecules having nonpolar nature can get into the cavity preferably, right? And outer surfaces are left for the environment. And you can capture the nonpolar molecules easily and you can isolate them from the medium, whatever you are dealing with. So, it is a huge development from 1905 to 1981. Afterwards, Leil Isaacs has done a lot of work on this. He has opened the structure and looked at the conformational analysis of this, how flexible are they, how you can rigidify them and so on. So, you can also make larger cucurbitural families, right? And Kim-Moon Kim is another person from Korea. He developed this unit to a larger cycles, macrocycles, wherein he can hold not one, two of or three of such molecules within the cavity. Okay. And when you do that, you can do a very specific reaction between these molecules, which is otherwise not possible in solution because molecules are random in motion. They are moving around all the directions. But if you confine them into a specific cavity, defined size, then you can do exactly the reactions that you want it to be. Okay, so it's very, very specific reactions you can do. That is the advantage of such kind of skeletons, which is demonstrated by Kim-Moon Kim from Korea, post-tech. Okay. Then there is, yeah. Huh? Behr is the first man who synthesized, yeah.
It's not like cryptide, it's not a
No. It's a scientist name who first made this. He was clueless as to what happened, but over the period of time, the structure of the same unit was revealed, and we know now there is this many number of glycoural units holding this many number of methyls. Okay, the chemistry was so old, but in olden days there was no clue as to what was going on. Okay.
Sir, can you please explain again the functions of cucurbitural, the pumpkin structure, sir?
Yeah. So the top portion that you are seeing, they are endowed with carbonyl functionality. These carbonyls are of dipolar in nature. Similarly, so this end is polar as such, and the bottom surface or the bottom rim is also polar in nature. But the internal part of it, right, is hydrophobic. And due to these reasons, it can hold only hydrophobic molecules within the cavity. Okay. So there is another structure which is as old as cucurbitural, which is called cyclodextrins. Okay. First made by Schrödinger, and later on you see a lot of developments starting from alpha cyclodextrin, beta cyclodextrin, gamma cyclodextrin, varying the number of glycoural units on the periphery. So this is holding this D-glucopyranose unit, glucose units, okay, and they are connected at 1 and 4 positions of glycoural units. You have 4 of these molecules surrounding 6 of these molecules connected, 7 of them, 8 of them, and so on. So depending on the number of glycoural units, they have tried to vary the size of the cavity. So if the cavity is small, it can hold small sized molecules. If the cavity is larger, you can have 1 or 2 number of small molecules, but 1 large molecule. Okay. So the cavity could be modified, size could be modified depending on the synthetic route, number of glycoural units that you are putting. So the void, as you are seeing here, it's typically 1 nanometer. Okay, gamma cyclodextrin. This is a gamma cyclodextrin which has 8 glycoural units, has a diameter of about 1 nanometer. So if a molecule has a size of close to that, say 0.8 nanometer or so, it could be nicely fit into this cavity. And the internal part of it anyway is hydrophobic, and the peripheral ones are hydrophilic because those are endowed with hydroxy functionality. Hydroxy groups are polar, and it has a capability to exhibit hydrogen bonding as well. And internal cavity is hydrophobic, so you can put hydrophobic molecules into the cavity. Okay, and lot of that, see, this is a glycoural unit. Just the side view of the molecule. What you are seeing here is 1, 2, 3, 4 from this view. 4 of the glycoural units are tied to it. And for many a time, for a long period, there was not much chemistry developed on this skeleton because these are very polar molecules, and purification of them, synthesizing them, characterizing them is very, very difficult. So recently, and there was not much chemistry known for capturing the cations. Okay. So what Professor Stoddard did, he is also a Nobel laureate, particularly for molecular machines. What he did was he just tried to mix this compound with a potassium salt and a dicarboxylic acid, and he made a nice structure. He encountered a nice structure such as this, which is forming a cage type of structure or a tunnel, tubular structure. And you can imagine there is a tube coming from the top, green, right? And it is extending through this yellow, and there is a tubular structure that is generated in this direction, right? And they have junctions. So this is another one which is going perpendicular. So it is a pipe junction that you will see, right? 3 of such tubes are interconnected and there is a junction, and such structures are nicely generated by the help of potassium ions. Okay. So this is a very first structure which is reported in a very excellent journal by Professor Stoddard, right? So he calls this as a metallo-organic frameworks, because he uses potassium as a salt, and he builds this organic framework using simple metal and a polar solvent, mixes it, finally this molecule crystallizes and they form nice tubular structures. And he has used this for gas adsorption studies, okay, because there is a nice cavity generated and you can absorb these gases, pass them inside, right. So it can hold huge density of gaseous molecules, small molecules such as hydrogen, carbon monoxide. He has demonstrated the capability of these structures for application. Otherwise, it was mostly confined to doing some synthesis with these structures, doing stereo-specific reactions using these structures. So it was only up to that. Now he has demonstrated into even application level, where gas adsorption is one of the very, very important topic these days, right. So he has demonstrated it for the very first time. And this is the tunnel that I talked about, right. You can see the molecules that are incorporated into the tunnel, for which he has a crystal structure also, through which he can show nice molecules are trapped inside this tunnel section. Okay. Later on, few other modifications came up, and the structure that you are seeing here is made of 4 aromatic units. 4 benzene rings you are seeing there, calixarine, right. This is a reaction between a simple phenol and formaldehyde. Have you heard of bakelite synthesis?
Yes, sir.
No, bakelite is not bakelite.
We don't know what bakelite is.
So how does it form? You must have studied how it is forming.
We just know what
What bakelite is?
plastic element or two.
It is a resin, right?
Sure,
It's a resin. So how do you generate that?
polymer. So by repeating certain units.
That's a polymer, correct?
So by repeating these units, I guess.
What are these units?
Calixarines.
Not calixarines.
Bridgedarines.
You have phenols. Phenols, you react it with simple aldehyde, they undergo condensation reaction, liberating out water. Phenols with aldehydes. They would undergo condensation reactions, removing water molecule, right? Phenols having active sites. What are the active sites for phenol? OH is one of the sites, and you have learnt about electron donating group, activating, deactivation, and all that, right? So phenol is what? Hydroxy group is what in the phenol? It's acting as a donating group, or it's a donating group. So it is ortho-para directing, or it is meta-directing group? It is ortho-para directing group, right? So in the phenol, how many available positions you would see? How many ortho positions and how many para positions? 2 ortho positions and 1 para position. So these are the active positions wherein these aldehyde molecules can react, right? So they would form polymers. Once condensation happens, this neighboring phenol comes in and just forms a network, and they form a polymer, which is finally a resinous substrate whose color looks like this. Yeah, somewhat pinkish, right? But very viscous, I don't know what you can do with that. It's very solid, rock solid thing, right? But such is the resin that was isolated by Adolf von Bayer.
So is it like a super cool liquid kind of thing?
It is, but you may have to melt it a little bit, then you can coat it on surface and all that. Okay, they will mix it with some solvent, solubilize it, or spray coat it, right, on the surface. Then once it is dried, it sets forever, right? So that's a very resinous compound, and this was made by Professor von Bayer in 1872.
The same way as the agent.
Right? He was a scientist. He made this resin, but he didn't know what it is composed of and how it is formed, right? So whenever he repeats, he always gets this resinous substance. But you can imagine, it is in 1872, in 1970, so close to 100 years, right? So after 100 years, someone thought of it, what if I just block these available positions, available active positions. Phenol has 2 ortho and 1 para, right? Let's keep blocking the para, right? And then he isolated the only ortho positions are available. If you let the ortho positions alone free, then those 2 positions can undergo condensation reaction, and let's say the neighboring phenol comes, again it has only 2 available ortho positions, that would condense again with formaldehydes, again 1 more phenol comes, so it can form a oligomeric network. Along with that, you can have small macrocyclic ring compounds as well, right? He isolated the ring compound in a very small quantity, which he can crystallize, and he found that 4 of these phenols have combined through the methylene bridge.
So what's an oligomeric network?
Oligomeric means it's not a polymer, but a small combination of the segment, a part of the segment, part of a polymer. Right? Polymer, let's say we have n units. This could be up to 10, 15, it could be even longer, 30, right? So such a length, but it's a defined length. Polymer is, yeah.
So since they are at ortho position, since we are blocking the para, then won't there be intramolecular repulsions, and the rotation of the conformation will also be very, very restricted.
Rotations are all possible, and that's when.
I mean, they should be very restricted. There's a lot of steric interaction happening.
No. The structure as such, if you look at this particular structure, this is the phenolic oxygen. That is the benzene ring. Okay. The available ortho positions are this site and this site. Para he has blocked using the tertiary butyl group, the alkyl group, the bulky alkyl group, right? So the available positions are only these 2, and the formaldehyde condenses at these 2 ortho positions and forming a cyclic structure.
I was a little confused because I saw the next one and
next one we will talk about a little later. Okay. So here, along with this, of course, he got some oligomeric products, because there can be free rotations possible along this. These 2 are the phenyl rings, let us say you are connecting them with the methylene bridge, they can go this way, that way, right? Once 2 forms, then 3rd one comes, 4th one comes, 4th one and the 3rd, the number 1 need not combine. There are free rotations, and they can form an oligomeric product, right? But a small portion of it formed the macrocyclic one, and the bottom part of is having the hydroxy functional groups, and they can establish a hydrogen bonding network between themselves. So it is an intramolecular hydrogen bonding which holds this 4 rings like this, right, and keeping the tertiary group at the periphery. So on the top of it you have tertiary butyls, at the central part you have the arene, and at the bottom part you have the hydroxy groups, right, holding it a crown type of a structure. Now what it can give you is, this portion is hydrophobic, central core is hydrophobic, The bottom portion is hydrophilic. Okay. So peripherally, it is completely modified. Structurally, you have modified the nature of the previous macrocycles by incorporating the aromatic unit. Okay. This was done by David C. Gatsche. Yeah.
So how are you blocking the para position, sir? So what are
We are placing the tertiary groups at the para position of the phenyl. So you can imagine the structure. Just write the monomeric unit. From here you can extrapolate. See this? Right? So I take this phenol only, right? And then react it with formaldehyde. Okay? So it condenses. 4 of this unit forms a cyclic structure, and hydroxy group is there at the bottom. The tertiary butyl groups are located at the top. Right? So it's a tetrameric macrocycle forming a crown type of a structure.
Yes, sir. Okay.
Yeah.
Sir, before when we talked about
Cucurbitural.
we said that the both sides had polar,
Correct.
and in the middle it was non-polar, and that allowed us to do certain to select for certain chemical reactions. Is there anything special that calixarine can do, like in terms
Calixarine can incorporate aromatic skeletons within its cavity because of the pi-pi interactions that it can exhibit. You understand? So each of the macrocycles are designed for some upgradation. That is the evolution that you are seeing, right? So in this case, next macrocycle, resorcinarine, 1,3-dihydroxybenzene is called as resorcinol. Dihydroxybenzene, right? It is a resorcinol. So the basic unit is resorcinol here, and then that is made to react with aldehydes, various aldehydes. It could be alkyl aldehyde or aromatic aldehyde, whatever. And again, tetracondensation happens, 4 condensation, to form this macrocycle. Right? Now in this macrocycle, the rim that is wide open, right, has hydroxy functionalities establishing hydrogen bond. Unlike the narrow rim having a hydrogen bond here. Can you visualize that? This is drawn like this. You must have to flip it and view that way. So you have the hydroxy groups on top. How many hydrogen bonding is possible? 1, 2, 3, 4. There are 4 hydrogen bondings possible, holding the rim by only hydrogen bonds, but the bottom portion of it will have only this R group that are pointing downwards. Correct? So now the surface is modified. The open surface was hydrophobic here. The open part is now made hydrophilic by establishing a hydrogen bonding network at the top, right? And if you put this molecule simply in water, 8 of these molecules come together to form a nice cage, spherical cage. Okay? That is characterized only by mass spectrometry and also by NMR analysis. Nuclear magnetic resonance spectroscopy and single crystal X-ray diffraction.
Sir, can you repeat it slowly, sir? It's very magnetic resonance. Oh,
Nuclear magnetic resonance spectroscopy. Through that you can characterize 8 of these molecules have come together. Okay. You can also discuss through mass. You can do a mass analysis of the sample, wherein you find 8 molecules have come together to form a spherical cage. People have also crystallized this octamers, right, which has only this cage type of structure by only hydrogen bonding. So 3 of the methods have proven that such spherical cages can exist only by a hydrogen.
So how exactly do the 8 species combine together to form such a compound?
8 species.
Yeah, no, you said 8 resorts and arenes come together to form an octamer, right?
Yeah.
Structurally, how does it look like?
So you can imagine like what we had in the previous case, the tubular structure, right?
Yes.
So similarly here, how you can imagine is say one resorcinarine from this side, another resorcinarine from this side, another resorcinarine from the top, another resorcinarine from the bottom, and from one from here and one from not 8, then we 6. 6 of them, right? 6 of them form hydrogen bonding network, and
Yeah,
exactly.
That's what I said.
Exactly. So it's a similar to that of the tubular structure, but here the bottom part is narrow, so it would appear like a cage, a spherical, near spherical cage, I would say, right? So that is the organization that you would get. This is shown, and people have done reactions within that small cavity that is available. Okay. Yeah.
What do we use these bridged arene macrocycles for, sir? So, what do we use resorcinarine for? Is it like bakelite? Is it similar to the functions of bakelite, or?
No, these molecules are mostly used for host-guest interaction studies, like molecular recognition purposes. You can, because these have pi surfaces, you can use it to recognize some pi, aromatic scaffolds. You can use it to recognize aromatic scaffolds, and that's the benefit of that. Later on, I mean, in recent days, I would say, these skeletons are very much useful in even column chromatography, where separation techniques you must have studied, right?
Oh,
Column chromatography techniques.
long strip.
Huh?
It recognizes the different.
Yes, because this gives, this bottom part of it gives a polar surface. So you anchor to the solid matrix at the solid backbone, and these hydroxy groups are available. If there is a hydrogen bonding substance in your mixture or a polar substance in your mixture, they would get incorporated to it or bound to, or they will be bound to it quite strongly than that of the non-polar ones. So the non-polar ones are let pass quickly, and the polar ones are bound strongly. After all the non-polar substances are let out, you can pour the polar solvent and collect the polar entities later. Okay, so these are the recent technological advances that is happening in recent days. People have also used these macrocycles to deliver drugs.
How, sir? Oh, because it's polar.
Yeah.
Take the drug.
Yeah, it would capture the drug molecule and then it be injected along with the, it acts as a delivery vehicle in the simplest sense. So it would carry the drug.
How do you release the drug?
Exactly.
Yeah, so that it is pH dependent, right? So at the target there is a switch of the pH, and that disassembles this and liberates the drug alone. So it can be made target specific. Okay, so these are the recent advantages that is happening with these kind of macrocycles, and drug delivery is one of the aspects, and chromatographic separation technique is another aspect. Okay, so likewise catalysis is another aspect. Stereospecific reactions are another aspect of this. So these are some of the advances that you're seeing in recent days. Host guest study. It's a recognition, molecular recognition. So another person came, this quite recent advancement in the macrocycle. He used 1,4-dihydroxybenzene instead of 1,3-dihydroxybenzene. Okay, para 1,4-dihydroxybenzenes. He started off with 1 and 4 positions dihydroxybenzene, and
That's not a hydroxy group.
it's not hydroxy. He started off with hydroxy,
Then generalize.
and then you alkylate it, so it gets alkylated, right? So he starts off with phenols first, dihydroxybenzenes, and then through this again same condensation reaction with formaldehyde, which forms 5 of this 1,4-dihydroxybenzenes come together to form a macrocycle. And now this macrocycle looks like these are like pillars.
Yeah, yes.
These dihydroxybenzenes are like pillars connected via this methylene bridges. Now that's why he called it as pillar arene. Okay. So then you can alkylate. You can modify this peripheral functionalities and then make it a little more non-polar so that you can purify, process them easily and so on. Okay. So this is a new type of macrocycle which is synthesized by a Japanese scientist who is Ogoshi. Right. Later on, people thought of developing dissymmetric versions of arenes. So they want to make it a little more chiral. Yeah.
So when you're forming these pillarenes or resorcenes, all of these, right? It's all condensation reactions by reacting phenols with formaldehyde. Right?
Correct.
So, but what difference do we make to arrive at these different compounds? Right? Like if you just reacted with formaldehyde, you won't get the compounds that we need, right?
You may not get in the very beginning. Okay. Our laboratory had we also went through the same kind of problem. It doesn't form because always you will get the oligomeric or the polymeric products rather than your desired macrocyclic compounds. Okay. So it's about now balancing to form this over that or that over this.
What do we do to make sure it produces more of these required macrocyclic compounds rather than oligomeric compounds?
The simplest strategy that one can easily think of logically is that you dilute it. Right? The reaction medium you just dilute as much as possible, which means you are going to have very low concentration, wherein this moment one condensation happens, it should not find immediately the other monomer.
Yes, sir.
Right? Thereby you decrease the polymerization rate.
So then by that logic it should be infinitesimally diluted.
Dilution, yeah. So we will mostly rely upon this concentration only. It's the best way to form to improve the macrocyclic yields, instead of arriving at the polymeric and the oligomeric products in major quantities. So you should not have a neighboring counterpart immediately to undergo reaction and then produce polymer. So let's say if dimer is formed and they would move around slowly and just wait until it meets the another dimeric counterpart probably, and then it condenses to form the macrocycle. So if it is highly diluted, then you can maximize the yields of the macrocycles. Okay, that's one of the ways that commonly being implemented. Okay, yeah. So another derivative is tetramethoxyresorcinate. How do you synthesize this? Is you start from methoxyphenols instead of starting with 1,3-dihydroxybenzene. So you protect it, you convert it to methoxyphenol, and then use that to form the macrocycle. Now you can arrive at tetramethoxy, tetrahydroxy cyclophenes, right? So what is the beauty in this skeleton is, you can view this molecule in two different ways. So if you are seeing like this, let us say, if methoxy is arranged, if you are going via methoxy, then it is clockwise arrangement of the methoxy, right? If they would have condensed and you would have gotten another product where methoxys are all located here and hydroxys are all located on the methoxy sides. So you can have a cyclic arrangement of, clockwise arrangement of the methoxys. You can also have an anti-clockwise arrangement of the methoxys. So these two are isomeric, enantiomers otherwise. Okay. So you can, if you separate them quantitatively, you can get chiral molecules as such. Okay. So that is with that motive, this molecule was synthesized, which is tetramethoxyresorcinate, and there are several groups who are working on it actively.
So then what does their hybrid look like?
Hybrid in a sense? This is not a resonance hybrid.
They're different isomers.
Oh, they're enantiomers.
Such as, enantiomers. If one is OR, another one is going to be S. If you label them as P, the another isomer is going to be M. Okay, so that is the relationship. You can separate them. You can form diastereomers, you can separate them, and you can have it chiral recognition can happen using these macrocycles. Okay, so that's one way that this was designed. You can also replace all the aromatic units using a heteroaromatic units. All these story have come. You can talk about pyrols, pyridines, imidazolium, indole, benzofurans, so on and so forth. Right? People have made a lot of this. The good thing with these heteroaromatic units are, okay, it can sense anions instead of the cations that you had with the other macrocycles. Okay, this calyx pyrrole, if you look at Sessler's papers, Jonathan Sessler, right? Look at his papers, he has used this to sense various anions, fluorides, chlorides, right, iodides. Lot of these anions were recognized using this scaffold. You can capture these anions as well. Okay, why this has taken up a big attention is because fluorides in water, right, there is a rule to maintain certain concentration beyond which it is toxic to human. So fluorosis is what we study, right? So those are the implications. So here, if you have such macrocycles and just pass this fluoride contaminated water, these macrocycles would capture fluoride ions and hence it decreases the concentration of fluoride in the water that is getting out. Okay, so this all the heteroaromatic macrocycles have this benefit of recognizing the anions.
So, heterocalyxanes are derivatives of tetramethoxyresorcinate.
No, no. These are all modified versions of the aromatic system that you are seeing there. Yeah, modified versions. You are replacing the simple benzene by a heteroarene, right? Pyrrole here and the central part here. See, they are very analogous. Compare this unit with that. It's analogous except that you have nitrogen here. So this nitrogen containing arene is called a pyridine, right? So this is a pyridine. So it is called calyx 4 pyridine. 4 of these pyridine units are coming to this.